So we have done Fourier series, we have done a bit of analysis, some examples. And in Fourier series, we basically have these two equations, the census equation and the analysis equation. And it's a kind of a thing wherein your census equation, it involves the use of coefficients a of k. And a of k, these coefficients, you in itself internally derive it from your input signal x of t. So there's a kind of a bilateral dependency, and this kind of behavior we show in the form of a notation. Fine. So if I have a signal x of t, obviously since you're talking about Fourier series, so x of t has to be a periodic signal. So we have x of t, it is a periodic signal with some period, say t. Fine. And corresponding to t, it has some fundamental frequency which is related to t, like this. Right? Then the Fourier series coefficient of this signal, which is denoted by a of k, this is the notation we have been using. This is the Fourier series coefficients, and we basically calculate these coefficients using the signal x of t. Right? So this kind of dependency we show in terms of this notation, wherein we say x of t, then use a bilateral arrow, a of k, Fourier series. Right? We often use this kind of notation. Right? So it kind of shows the dependency. Using x of t, you calculate your coefficients a of k, then you use these coefficients in the expansion of x of t as per the Fourier series. Okay? So in this video, we'll be starting with the what you call different property. We will be discussing some properties of continuous time Fourier series. Right? Few properties. And we'll be starting with the first property, that is a property of linearity. Right? And a linearity states that if I have two signals, x of t, which is related to the coefficient a of k through the Fourier series like this, then we have another signal y of t, which is related to Fourier series through the coefficient b of k. Okay? But the thing is that both x of t and y of t, they are periodic signals. So both, it's a given because you're talking about Fourier series. So jo bhi signals hongi, they have to be periodic. Right? So the thing is, both x of t and y of t, they are periodic, which is expected, are periodic. But what is important is they have a common period t. Fine? Means both these signals, they have a common period t. Right? Now since x of t and y of t, they have the same period, it means that any linear combination of the two signals will also be periodic with the same period. When we actually started the discussion on, if I remember, if it is here, on the Fourier series, we did a bit of analysis wherein I expressed a simple exponential. And from this we got the harmonics. And we concluded that this is the signal. That is, if you compare this and your normal what you call exponential signal, they are related with the period, like I have written here, they are periodic with period t. Fine. So fundamental. So the thing is that if you have two signals and they are periodic with the period t, and if you construct a new signal which is a linear combination of these two signals, it will also have a period t. Fundamental periods, they may vary. X of t may have a different fundamental period, y of t may have a different fundamental period. Fundamental period means the smallest value of t for which a signal repeats. and then when you form the linear combination of these two signals, it may have a different fundamental period. But the thing is that they all will be periodic with the period t. Okay? So if I define a new signal as a linear combination of these two signals, so suppose I define, let's say, z of t, it is defined as linear combination. Linear means you have some constant a and b like this. Fine. So we have defined a new signal which is the linear combination of x the two signals which have the period t. Fine. And now let's suppose iska Fourier series, it has some constant, say c of k. Okay. Then from the linearity property, it is easily extended that this c of k, so let me just put it like this way, z of t has been formed using a linear combination of two periodic signals with the same period, and when we take the Fourier series, it will give a coefficient c of k, which will be actually the linear combination of these two coefficients. It should be remembered, this will also be periodic with period capital T. Okay? So this is the linearity property of the Fourier series. You don't need to prove it, it just follows from the linear discussion. And we have already proven it that if you have two periodic signals, unka jo linear combination hoga, it will also be periodic with the same period t. We have not generally proved it, but we have proved it in with respect to the exponential signal, and in general you can apply this thing. Fine. So this is the linearity property, but more importantly, we are interested in our basic properties. We are interested in what happens to time shifting in Fourier series, in the frequency domain as defined by Fourier series, right? Because shifting, scaling, time reversal, these are some basic operations that are inherent in signal processing. So let's see what happens to time shifting in the Fourier domain, right? Now when a time shift is applied to a periodic signal x of t, if you remember, shifting only shifts the waveform either to right, either to left. It does not alter the shape of the waveform. Means by now you must have understood it because we have done it a lot of times. So if this is my sinusoidal signal, this is its time period, say t. Now if I shift it either to right or to left, let's suppose I have shifted it like this, right? But the period still remains the same, right? So time shifting, it does not alter with the period of the signal. हाँ, अगर ये स्केलिंग होता है, टाइम स्केलिंग, जहाँ पे आपका सिग्नल either expands या either compresses, so that may affect your period by some factor, by the scaling factor. We will discuss it separately. But as far as shifting is concerned, it does not, it only shifts your waveform, but it keeps your waveform intact. It doesn't expand it, it doesn't compress it. So the period will not be affected. Fine. So as far as this property is concerned, if I have a signal x of t, fine, and it is related through Fourier series to the coefficient a of k through the Census and the analysis equation, then if I define a signal y of t, which is a shifted version of the signal t minus of the signal x of t. Now, because shifting does not alter the time period, so x of t and y of t, they'll have the same time period, capital T. If I assume that x of t is periodic with the period t, so it will be presumed. Now I'm interested in finding this, that if y of t is related through Fourier series to some coefficient, say b of k, how are these two related? Fine. In other words, what happens to the coefficient of a signal if it is time shifted by some amount, in this case t naught. So we will do a small mathematical analysis It is pretty straightforward. Now b of k, it can be calculated using the conventional integral over the time period t, because y of t is x of t minus t naught, and we have jk omega naught like this. And if I make a small substitution here, just a mathematical substitution, I defined a parameter tau as t minus t naught. And if I take the derivative on both sides, d of tau is equivalent to d of t. T naught is a constant time shift, which means I can express b of k as 1 upon t integral over the time period t x of tau e raised power minus j k omega naught. T की जगह I will write tau plus t naught, and dt की जगह we have d tau. Then I can do some mathematical manipulations. 1 by t stays at it as it is. I will take that constant term outside, k omega naught t naught, and internally my integral will be t for the time period t x of tau e raised power minus j k omega naught tau d of tau, okay? Which means b of k is equivalent to, this is the extra term, e raised power minus j k omega naught t naught, and internally I have this thing, omega naught tau d of tau, right? Now this part, okay, I forgot 1 by t, and one thing, I will include 1 by t here. Okay, now this part, this is actually the coefficient a of k. The only difference is instead of t, because अगर आप ये coefficient calculate करेंगे, it will be 1 by t, because time period is same in both the cases, over the period t x of t e raised power minus j k omega naught t d of t. So इसमें they are quite similar, only difference is the way we express the parameter t. But the thing is, t also represents time as a continuous variable. Tau also represents time as a continuous variable. So this is very much the coefficient a of k, which implies that b of k is related to a of k using this factor. Okay. So if I put it in a better form, what we have concluded right now is this, that if I have a signal x of t, it is related through Fourier series to a coefficient a of k. This x of t has a time period t. Then if I shift this signal, first thing is there will be no change in the time period, so it will still have the time period t. Then it will be related through Fourier series to a coefficient b of k, which is related to a of k using this expression. Okay? So this is the relation. Now additionally, you see you have b of k, you have e raised power minus j k omega naught t naught ak. If you take magnitude on both sides, turns out k omega naught t naught magnitude and a of k. Now this is a pure exponential. The exponential ka magnitude is always unity, which means magnitude of b of k is the same as the magnitude of a of k. Okay. So whenever a periodic signal is shifted in time, the magnitudes of its Fourier series coefficients, they remain unaltered. उसमें कोई change नहीं आएगा. हाँ, in general, they will be related like this. So magnitude wise, they will stay the same. Okay. So this was the second property, the time shifting property. Then on same grounds, we can define the third one, the time reversal property. Fine. Again, if you talk about time reversal, it doesn't alter the period. ये आपका normal signal है. If you time reverse it, so I think it will be like this. So again, span is the same, time period t, time period t. So if I have a signal x of t, it has a time period t. Then if I define a new signal y of t, which is the time reversal या folded version जैसे हम कहते हैं, so it will also have the time period t. Right? Now we want to see what happens to the coefficient. So again, we'll do a bit of mathematical analysis that I have x of t. You can express it as a Fourier series minus infinity to plus infinity. It is the general census equation. E raised power j k omega naught t. Fine. Then I can define y of t, which is nothing but x of minus t, as summation k running from minus infinity to plus infinity a of k e raised power minus j k omega naught t. And again, if I do a bit of mathematical manipulation, say suppose we substitute k is equivalent to say minus m, okay? तो उस हिसाब से we'll get y of t is equivalent to x of minus t is equivalent to summation m runs from, it will be infinity to minus infinity, but it is the same thing as writing minus infinity to plus infinity, a of minus m e raised power j m omega naught t. So if I call this 1, if I call this 2, now if you compare these two, equation 1 and 2, they have the same exponential parameter, they have the same limits, just that a of k is equivalent to a of minus m. So I can generalize here that if x of t after Fourier series is related to a of k, then x of minus t, that is the time reversal version of this signal, it will be a of minus k. Again, it is minus m, but m and k, these are just variables, they actually represent time, so we can use this kind of alteration. Okay? So it means that the time reversal that is applied to a continuous time signal, it actually results in a time reversal of the corresponding sequence of Fourier series coefficients. ठीक है, तो टाइम शिफ्टिंग में हमने देखा, इफ़ यू टाइम शिफ्ट योर सिग्नल, जो corresponding what happens with the Fourier series coefficients is that it gets multiplied by an exponential factor. और टाइम रिवर्सल में हमने देखा कि इफ़ यू टाइम रिवर्स, इफ़ यू फोल्ड योर इनपुट सिग्नल एक्स ऑफ टी, आपके जो कोफिशिएंट्स है they will also get folded because we are changing this subscript, k becomes minus k. Okay? So these are 3 properties. We'll stop here. Next video we'll take some more properties of Fourier series.